Okay, so here is the example number 2, and that says that function here is f of t equals to t to the power n, and we have to apply the Laplace operator onto this function. So our formula is given f of s equals to, that is Laplace of t. Laplace of t to the power n, and that is for integral from 0 to infinity e to the power minus st into t to the power n into dt. T to the power n here is f of t, so we replace it t to the power n. So how this integral can be solved? This integral cannot be solved by any means rather than the formula integration by parts, by the technique integration by parts. And the integration by parts formula is written in the top corner, right corner in the board, and that is u into v dash. One is a simple function and the other we have to take it a derivative if it can be integrable. That is equal to u into v minus integral u dash into v. You can also memorize any kind of, you can use any kind of formula that you have memorized before integration by parts. So here I am selecting this as v dash and it is selected as u because e to the power minus st can be integrable. So this is also integrable, but it is increased if I take its integral. So it can be reduced and this can not have any change in the integral or differentiation. So which is, u is selected as e to the power t to the power n, and v dash is selected as e to the power minus st. So I integrate it with respect to t, that gives me v, so that means e to the power st divided by minus s. Minus s here is a constant, so by integration constant is divided, and in the differentiation the constant in exponential and trigonometric function is always multiplied. So in the next step I am using this u dash, and that will be with respect to t, it becomes nt to the power n minus 1. So I am using this formula, and this formula generates 0 to infinity, and limits are 0 to infinity. So u into v is t to the power n e to the power minus st divided by minus s 0 to infinity minus integral from 0 to infinity u dash is n t to the power n minus 1, and v is e to the power minus st divided by minus s into t. And you know that n is also a constant and s is also a constant, so n by s does not have any effect on to this integral operator, so we take it out. So your integral becomes minus e to the power st into t to the power n divided by s plus n by s 0 to infinity e to the power minus st into t to the power n minus 1 into dt. Now you can see that the second formula is a Laplace transform of the function t to the power n minus 1 along with this term n into n by s. Now how to solve this integral? We again use integration by parts, and for integration by parts I again suppose v dash is equal to e to the power minus st, and u is equal to the power n minus 1. So u dash is equal to n minus 1 into t to the power n minus 2, and v is again e to the power minus st divided by minus s. That gives rise to this. So I use this form to make it, and I have to use these limits of integration as 0 to infinity. So that becomes minus t to the power n e to the power minus st divided by s from 0 to infinity, and plus n by s, and I have to multiply this. I have to here is t to the power n minus 1, and v is e to the power minus st divided by minus s minus integral n minus 1 t to the power n minus 2 divided by minus s e to the power minus st into dt. And one more thing, you can see that n minus 1 here is again a constant and minus s is also constant, so that makes it independent of the integral operator. So now this becomes, we will solve it later on and I will tell you how it is solved. This term plus n by s t to the power n minus 1 e to the power minus s, and you can see that it yes, minus n by s square, and if it is multiplied with this term then it becomes minus minus becomes plus, so n by s square and n into n minus 1, and the integrand remains t to the power n minus 2 e to the power minus st into dt. So that is the integral operator of Laplace of t to the power n minus 2. It means that by using the integration by parts again and again, your function t is reduced by its power n minus 2, n minus 3 along with these terms. Now these terms have this very strong pattern, and the strong pattern is, so by ignoring these are the integrand terms, so you can see that by gradually multiplying and by gradually decreasing this term, you can watch the pattern of your selection, pattern of your major terms, and that is 1 by s, then n by s square, and n into n minus 1 by s square. So that gives rise to the fact, the general formula, and the general formula is here n into n minus 1, the next will be n into n minus 1, n minus 2, n minus 3, and so on. So your denominator becomes, I will write it only the two terms, and the two terms are here in this. I will use this formula again. So we will generalize by using this formula, and this formula says that minus t to the power n e to the power minus st divided by s plus n factorial divided by, if it is integrated by parts again and again, then it becomes n factorial, n into n minus 1 plus n minus 2 and so on, divided by s into s square into s cube into so on. So first term is n by s, second term is n into n minus 1 by s square, and again by integration by parts the constant term is n into n minus 1 n minus 2 by s cube. So you can see the pattern behind this is, if n is 1 then it is s to the power 1, and if it is n is 0 then s to the power 1, and n is here it is 1, so that is s to the power 2, and if n is here highest term is 2 then it is 3. So in the generalized kind of term is n factorial by s to the power n plus 1. So that is the Laplace transform, s to the power n plus 1. So this is the Laplace transform of this. Now we come to solve this limits of integration, and I will tell you that these, by using these limits of integration, upper limit and lower limit, it becomes, these two terms are vanished and only remain, we are left with this term. So solve, you can apply upper limit minus lower limit. So I have to transform this e to the power st in the denominator to avoid the negative, to avoid the infinity in the but we cannot avoid here. So we have infinity to the power n e to the power infinity into s, minus 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 becomes plus, and it becomes 0 to the power n e to, instead of t you have to replace it, so e to the power 0 into s. Okay, now these two terms, 0 to the power n divided by 1, that becomes, does this become, this infinity to the power is infinity and e to the power 0 is infinity. So by comparing these two terms we can see the gradual dominant term. We can check the reaction of or dominance of a gradually rapidly increasing term, and from the graph you can see that graph says that the exponential function grows rapidly than this function t to the power n. So this function gradually, the dominant function here will be e to the power infinity, and that becomes 1 by infinity into s. That makes it 0 plus 0 plus n factorial by s to the power n. So this is a very important point by using the dominant term technique. So e to the power t is a dominant term, so that is why we have to follow e to the power infinity is equal to infinity, and that terms remains the same. So this is t to the power n. So this doesn't have any effect on the whole term, but e to the power t has the major effect. So we are left with n factorial s to the power n plus 1. So that means Laplace of function t to the power n is n factorial s to the power n plus 1. We have derived the generalized type, and if we have the specific type, then you can use any constant. You can replace any constant, like Laplace of t to the power 9 is 9 factorial divided by s to the power 10. And also any other example, Laplace of t to the power 5, that is 5 factorial, that is to just apply the formulas, and if no formula application is required, then you have to just apply this direct formula and find out the Laplace operator or Laplace transform of any kind of functions like this or like e to the power at. This.